Okay, so we're going to continue our discussion um, about the standard atmosphere. Okay, so um, in this lesson, we have three learning objectives here. You're going to explain the temperature and pressure variation in different altitude and describe this this variation in terms of specific weight, the lapse rate, or the rate of change of temperature that corresponds to the altitude, and also with the utilization of the ideal gas or the perfect gas equation. And lastly, you're going to explain the physical relationship of quantities, as expressed in the following equation. So we have here the first equation that refers to the variation of pressure in accordance with the change of elevation, the dz, okay, with the use of the perfect gas equation or the ideal gas equation. The second equation refers to the temperature variation. Okay, the temperature variation or the change of temperature as we move from the lowest point of the atmosphere going to the highest point of the atmosphere. Okay, and also the third equation is the equation that describes the change of pressure as we move from the surface of the earth going to the upper part or the highest point or to any point in the higher elevation in the atmosphere. Okay, so as you can see, we have a lot of symbols or quantities here in the equations, and then we're going to describe those quantities later on in this discussion. Okay, so let's proceed. So, standard atmosphere. Okay, it is important to establish this idealized representation of meaning the average condition, in the Earth atmosphere. Okay, this is for the utilization of different industry that involves in designing aircraft, in the space or spacecraft. Just like as you can see in the slide, we have here the space shuttle, the Dragon. I don't know what do we call this. This is designed by SpaceX, and the missiles. Okay, so the concept of standard atmosphere is so essential for the design of this particular spacecraft. Okay, so commonly we describe pressure, okay, in terms of the temperature or some other specific condition, and also we use reference pressure, but this is not always available if we are talking about conditions, in the atmosphere, in the Earth atmosphere. That is why it is important that we have to establish this what we call the standard atmosphere, right? Meaning a particular condition that is true all year round. Okay, the condition of the atmosphere. Okay, now let's proceed. So, what is this standard atmosphere? So the standard atmosphere is the currently accepted standard, okay, that is based on a report published in 1962, matagal na, 1962, and was updated in 1976, medyo matagal na rin. And they call it US standard atmosphere, okay? And as what I've said, this is the idealized representation of middle latitude, okay, year-round mean conditions of the Earth atmosphere. So we have here in the table the properties, okay, of US standard atmosphere at sea level. Now take note that the temperature is expressed in Kelvin, okay? 288.15 Kelvin. The equivalent of that to Celsius is 15 degrees Celsius, right? And okay, those are the magnitude. So at sea level, the temperature that we're going to use must be 288.15, right? That's the standard. And the pressure should be 101.33 kilopascal. Okay? Or actually, that is the 1 atmosphere. Right? And the density of air at sea level is 1.225 kilogram per cubic meter. Alright? And the specific weight is 12.014 Newton per cubic meter. And the viscosity is 1.789 times 10 to the negative 5 Newton times second per square meter. So these are the quantities that we are going to use. Okay, if we're going to deal with the standard atmosphere or the US standard atmosphere, all these measurements are at reference at sea level, meaning the Z is equal to 0. All right. Now, take note that the gravity is not included in the it's not stated. I mean, it's not stated in the table. However, we understand that the gravity at sea level is equal to 9.8 or 9.807 meter per second squared to be exact. Okay? So, we understand based on our basic mechanics that if we change our elevation from the surface of the earth going upward, the rate of gravitational force is also changing. Diba? So we understand that. However, the difference of these forces, okay, of the gravity is considered insignificant. The changes, the difference. That is why they advise by this standard atmosphere that the magnitude that we're going to use all throughout the computation using the standard atmosphere must be at 9.8 meter per second squared. We are going to disregard the differences, okay? Because the difference or the differences of this magnitude is insignificant according to them, okay? According to the standard atmosphere, right? So in the computation, we will be using 9.8 meter per second squared, even it is at the highest elevation, okay? Now let's proceed. Now here, as you can see in the slide, is the graph that describes the temperature, the average temperature of that particular elevation or altitude, and its corresponding pressure. Okay? So, it is shown that from the surface of the earth, as we move towards 10 kilometers, that is actually the troposphere. Okay? So, the pressure is changing. Okay, the pressure is diminishing. All right, and if we're going to look at it, we understand that the amount of molecules, as we discussed before in our previous discussion, is actually the amount of matter, okay, is going less. Okay, the density is going less as we move up, no, in a particular elevation. That is why here it is shown that the average pressure is also changing as we move higher to the higher elevation. Okay, so this is the recording. Now take note that at stratosphere, at this part of the atmosphere, there is no change. There's no significant change. Okay, of temperature at this point. It maintains to negative 56.5 degrees Celsius. Okay, so in this particular reading, they use Celsius, but if we're going to have our computation, we have to change Celsius into Kelvin to conform with the other quantities. Okay, all right, so this is how the temperature changes and the pressure changes as we move from different altitude. Okay, you're just going to look at or just going to have a screenshot. I don't worry, I'm going to upload a file of this so that you can look clearly. You can look at the magnitude in detail, right? So this is the variation of temperature. As I've said, this is the variation of temperature corresponding to its altitude, no, based on the US standard atmosphere. So the temperature decreases, okay, with altitude in the region nearest to the Earth's surface or the troposphere. Then it becomes essentially constant in the next layer in the stratosphere, as what I've mentioned a while ago, and starts to increase in the next layer. Okay, so from the surface of the Earth, the temperature is decreasing. At the stratosphere, it remains constant, and as it moves from 20 kilometers upward, the temperature is starting to increase, gradually changing. All right, so that is the condition, that is the behavior of our atmosphere. Let's proceed. Okay, now if we're going to describe that, or if we're going to determine the temperature at a particular altitude, we need this particular equation. Okay, this equation, that is temperature is equal to the absolute temperature minus the lapse rate times the altitude, okay, or the z. Okay, so this is the equation that we're going to use to determine the temperature change. Okay, let's proceed. Now, in describing the standard atmosphere, I mean, if in describing the atmosphere using the standard atmosphere, using this standard, we need to use the specific weight. Okay, the specific weight is actually the product of density times the gravity. Okay, and also, since we are dealing with gases, it is also important for us to use the ideal gas equation, which is density is equal to pressure over the gas constant times the temperature. All right. Now, we are going to use also the expression that we derived in our previous discussion. Okay, this one. The variation of pressure in terms of change of its elevation. Okay. So, this is the slide that we used, no, in that previous video. Okay, as to how we derive with this particular expression. Okay, take note that in this case we use y because we follow the y axis as the vertical change, but we're going to change this one now into z. Okay, to conform with the notations that the standard atmosphere is using. All right. So this is the equation that we derived previously. Okay. So again, this equation describes the pressure variation. Okay, at any elevation, considering that the density and the gravity is constant. All right. So what I've said a while ago, that even there is a change of gravity, but we will be using 9.8 all throughout, no, the 9.8 magnitude all throughout the computation. Okay, because the change of gravity is insignificant. All right. Okay. So let's proceed. Now here, now going back to that slide. Okay, so the specific weight is again equal to density times the gravity, and the ideal gas equation is equal to the ideal gas equation is this one. The density is equal to pressure over the RT, or the R meaning the gas constant, times the temperature. Okay, so we're going to fuse the two, okay, equation here. Okay, so this expression, we're going to rewrite this one into this form, but we have to change the y into z. Okay, and we're going to integrate the ideal gas equation in this part. That is why we come up with this equation colored red. So dP over dC equals negative Pg over RT. Okay, so in this expression, we describe the variation of pressure in terms of the change of the elevation, the z. Okay, and also we consider the quantities that is described by the ideal gas equation, meaning the gas constant, right, and the temperature. Okay, so this equation colored in red is now the equation that describes the pressure variation. Right. So the P here is actually referring to the absolute pressure. Okay, the G is the gravity, the R is the gas constant, the T is the absolute temperature, and the Z is the altitude. Okay, I hope that is clear. Now let's proceed. Okay, so the dP over dC equals negative PG over RT will be re-expressed using calculus. Okay, but at this point, we are not going to deal with how they come up with this expression. No, so we will just I will just show this one so that you will know what expression is that. Okay. Now, they fuse this equation, the equation of temperature, to this expression, and they arrive with this final equation, which is shown inside the box. Okay, so so pressure is equal to the absolute pressure times this expression 1 minus the beta, the lapse rate, times the Z, the elevation, the change of the altitude, and over the absolute temperature. Right? Take note that there is an exponent part here in fractional form, the gravity over R, or the gas constant times the B, or the rate of change, or the lapse rate. Okay, so this will be the equation that we're going to use to describe the pressure variation in the atmosphere. Okay, so in the computation, this will be the equation that you're going to use. Right, so I will give you a problem later on, and then you're going to use this equation to solve the problem. Right? Okay. Now let us try to look at the units. Okay, so that in the computation you will not be confused. Okay. So I make this as a practice because I noticed that some students don't know how to manipulate the units of the different quantities, and then this also will help us to understand how we come up with the final units here. So since we are referring to the variation of the pressure, so pressure, it should be in Pascal. Okay, and we are dealing with a lot of quantities. So how can we come up with Pascal? So we will that will be shown here in this slide. Okay, if we're going to look at it clearly, okay, here, the beta here, or the lapse rate, is expressed in Kelvin over meter. Okay, and the Z here, the altitude or the elevation, is expressed in meter, and the TA, or the temperature at sea level, is expressed in Kelvin. Right? The gravity, we understand it is meter per second squared, and the gas constant is expressed in joules per kilogram times Kelvin. Okay? Take note, there is joules here. Now, joule, or 1 joule, is equal to Newton times meter. And we understand that if it is Newton, it is kilogram times meter per second squared. Now, this will become kilogram times meter per second squared times meter. Okay? All right. Now, at this portion, all of the units in this part of the equation are cancelable to each other. Okay? So, the kilogram can be cancelled out. The meter per second squared and the meter per second squared can be cancelled out. The Kelvin, the unit Kelvin of temperature, can be cancelled out. And the meters, or the meter, can also be cancelled out. Okay? So all of the units that you can see here in the exponential part of the equation can be cancelled out. Right? Now, here, in this term, the Kelvin can also be cancelled out, and the meter can be cancelled out. So now what will happen to the unity after the computations here? There will be no units here now. Okay. So here the remaining unit is Pascal. Okay. So we understand that the PA, the absolute pressure, is equal to 101.33 kPa, or kilopascal. Okay. So yeah. That is the reason why we have the final unit as Pascal. Okay, I hope that is clear. Now, I have here a problem. So you are going to solve this problem using the equation that I discussed. Well, look at this one. Okay, this is the equation that you're going to use. Okay, so you are going to solve this problem now. Determine the pressure variation at the highest altitude of troposphere, that is about 11 kilometers above sea level, with the lapse rate of 0.0065 Kelvin per meter. And you're going to obtain the absolute pressure, the temperature at sea level, and the G, from the table below here. And of course, our gas constant is equal to 286.9 joules per kilogram times Kelvin. So you have to use the SI units for your solution. Now, you're going to write your solution in a yellow pad or in a bond paper. And then you're going to submit that one during our face-to-face schedule. Okay? So, we just able to discuss this equation, importantly this equation, okay, and also the condition of the atmosphere at different levels, okay, the standard atmosphere, okay, and also the other equations that we just described, those one, okay. So if you have questions regarding on this topic, you can message me privately or you can comment down below. Okay, that's all. Thank you.